Hi, thank you for visiting my poster. My poster talks about the photoemission from lunar surface. The sunlit lunar surface of the moon is directly exposed to the solar UV radiation and solar wind plasma. Due to dominant UV-induced photoemission, the sunlit lunar surface acquires a positive potential. Emitted photoelectrons and the local plasma population create a photoelectron sheath in the vicinity. Therefore, understanding the generation and energy distribution of photoelectrons from the lunar surface is crucial for studying the complex electrostatic environment surrounding the sunlit moon. To understand the photoelectron generation, consider the black line as a lunar surface. When a photon incident on the surface, the regolith work function determines whether the photon is energetic enough to emit a photoelectron or not. Electrons within the lunar surface lattice follow Fermi-Dirac statistics, and the regolith temperature decides how many electrons are available for photoemission. Those electrons hitting normal to the surface from inside of the lattice can absorb the incident photons. Based on the information of the quantum yield, there will be an outward photoelectron flux. As the surface loses electrons, the surface acquires a finite positive potential, which attracts some of the emitted electrons in the form of incoming photoelectron flux. So the net flux will be the difference between the two. Including all these aspects, the photoelectron distribution function will look like this. To derive the photoelectron distribution near the lunar surface, we have taken a typical solar spectrum from FISM 2 developed by Chamberlain et al. 2020. The regolith work function and temperature are taken to be 5 electron volt and 400 Kelvin respectively. Quantum yield is another important parameter. We have taken two widely used yield values. One is argued to be most probable yield for lunar surface reported by Walbridge 1973, and another is experimentally measured from the lunar sample reported by Wills et al. 1973. We have found that the effective photon flux which give rise to photoemission significantly depends on the quantum yield. The bottom left figure also shows that not only Lyman alpha radiation near 120 nanometer, but also high energy photons significantly contribute to photoemission. It is also noticed that the photoelectron distribution function significantly differs for different yield values. The photoelectron distribution function peaks around a particular photon radiation in terms of excess energy after overcoming the barrier height. The blue line represents the photoelectron distribution function near the uncharged lunar surface, which significantly differs from Walbridge to Wills et al. Yield values. It is also noticed that the lunar surface acquires a finite positive potential. The electrons have to overcome extra barrier height in addition to the regolith work function, and the peak of the distribution shifts with varying the surface potential. Lastly, I want to point out that the distribution derived using the Wills quantum yield closely matches the experimentally obtained distribution measured by Feuerbacher et al. 1972 when fitted using the photoelectron temperature obtained using Fermi-Dirac statistics. Thank you for your time.